Okay, so today we're looking at the vector product, which we've already covered a little bit in class. I'm just going to review the examples that we've already done and then continue through with the examples that we didn't get to. So, two vectors, provided they are not parallel, define a plane. A plane is a flat surface extending indefinitely in all directions. The orientation of a plane can be described by a vector perpendicular to the plane, known as the normal. The vector cross product is defined as the product of the magnitudes of each vector multiplied by sine of the angle between them and multiplied by the normal vector n. N can either be coming out of the page or going into the page, and we use the right-hand rule to determine that. So thumb points in the direction of the normal vector n, fingers point in the direction of the b vector, and the palm direction is of the resultant direction of theta. Note, because of this, the order of the cross product is not commutative. A cross B is equal to the negative of B cross A. So in example 18, we had these three vectors. We were asked to find A cross B and B cross C. So for A cross B, we multiply the magnitudes of 4 and 7 by sine of 60 degrees, the angle between them. And when looking at our right-hand rule, because we're going from A to B, our normal vector n is going into the page. When looking at B cross C, our magnitudes are now 6 and 7, and our angle is 142 degrees. So that's the sum of 60 and 82. But this time, because we're going from B to C, our fingers are going in a counterclockwise direction, which means the normal vector is coming out of the page. So both of these give us some coefficient of the normal vector and then two different directions. So for part A, it was into the page, and for part B, it was out of the page. For example 19, we're not given a drawing. We are just given two vectors in polar form. We're still able to find it, but then we have to do some visualization to understand whether it's going out of the page or into the page. So because we are going from a smaller vector to a bigger vector, we've got our fingers going to the left, which means the normal vector is coming out of the page. So that's 16.39 times the normal vector n out of the page. When applying this to I, j, and k form, we get the following properties. Any vector cross product with itself is 0, because the angle between a vector and itself is 0, and sine of 0 is also 0. Any vectors that are perpendicular to each other have an angle between them of 90 degrees, and then the normal vector is the third vector that is not described. So I and j cross product to make k, the third vector, because that is orthogonal to the point where I and j's tails meet. So applying this to all cross products possible, I and j, I and k, so far and so forth, gives us the following table. If we then apply that to A cross B, where A and B are in Cartesian form, we can find that distributing that cross product gives us the following products: 3i and 3j, 3i and negative k, 2j and negative 2i, 2j and negative k, negative 4k and negative 2i, and negative 4k and 3. So combining like terms and applying those cross products gives us 10i plus 11j plus 13k. By looking closer into this property, we can actually see that all we're doing is the same as finding the determinant of a vector with the first row as I, j, and k components, the second row as the coefficients of I, j, and k components of the initial vector, and the third row as coefficients of I, j, and k components of the second vector. For example 21, we applied that. So we constructed the matrix A with I, j, and k, 2, negative 2, 1, and 1, 2, and 3. And then finding the cross product is the same as finding the determinant of that matrix A. So finding those two sub-matrices and the determinants of those, we get a final answer of 8i minus 5j plus 6k. So we construct those I, j, and k sub-matrices based off the information covered on the previous page. An application of these cross products is found when looking at the area of parallelograms and triangles. So if we try to consider this parallelogram and its value of theta, sine of theta is the same as opposite over hypotenuse. Opposite to the angle is h, and the hypotenuse of the angle is b. So h can be defined by b and theta, and we get that when we go to our area of a parallelogram, substituting h as b sine theta, we get that the area of the parallelogram equals the magnitude of a times the magnitude of b times sine of theta, where theta is the angle between a and b. Something similar happens for the triangle, but instead of being the entire cross product, it is half of the cross product because the area of the triangle is half of the base times height. So when looking at example 22, if we were to calculate the area of this parallelogram, we're looking for the magnitude of A times the magnitude of B times sine of 60. That is going to give us 5 times 4 times sine 60, which is going to give us 17.32 square units. Okay. A similar process for calculating the area of the triangle OAB. If A is 2, 1, negative 1, and B is 3, 0, 2. So we're starting from the origin, we're going to those 2 points A and B. So our area is going to be half times the magnitude of A times the magnitude of B times sine of theta, where theta is the angle between. So finding the angle between these two is as simple as applying the dot product. But to apply the dot product, we first need to know what is the magnitude of A and B. So we'll start with that. The magnitude of A is equal to 2 squared plus 1 squared plus 1 squared. That's going to give us square root 6. The magnitude of B is equal to the square root of 3 squared plus 0 squared plus 2 squared. That is going to give us 9 plus 4, which is square root of 13. So to find cosine of theta, that is going to be the dot product divided by the product of the magnitudes. So the dot product for us is 2 times 3 plus negative 1 times 2. So that's 6 minus 2, which is 4 over root 6 times root 13. So theta is equal to, let me just check here. So that's going to be 63.07 degrees. So applying that to our formula, we get that A, the area, is equal to half of root 6 times root 13 times sine of 63.07, which is going to give us an area of 15.75 units squared. So some properties of the vector product. The vector product is not commutative. We've looked at that earlier. A cross B is not equal to B cross A. It's equal to negative B cross A. The cross product is distributive. So not distributive, associative. So A cross B plus C is equal to A cross B plus A cross C. A dot B cross C is equal to A cross B dot C. And then a scalar K times A cross B is equal to the scalar being multiplied by the entire cross product and also the scalar being multiplied by just B. So A, B, and C and all these are vectors, and K is a scalar. Okay, scalar triple product. So in the scalar triple product, any three vectors that do not all lie in the same plane can form a parallelepiped. The volume can be found by multiplying the area of the base by the perpendicular height. So the area of the base is a parallelogram. So the area of the base is a parallelogram, which is given by the vector product B cross C. The perpendicular height is given by A cosine theta. Therefore, the volume is going to be the magnitude of A dot B cross C. Where the quantity A dot B cross C is called the scalar triple product. Okay, so some things to note. The result is a scalar. Because we're taking a dot product after a cross product, our result is a scalar. Part 2, B cross C is a vector, so it must be calculated before the dot product, as a scalar cannot be part of the vector product. Determinants can be used to simplify the triple product calculation. So if we have A, B, and C, then A dot B cross C is equal to the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. And ultimately, this comes from the fact that if you were to do the first row as I, J, K, and then take the dot product, that I component would be multiplied by A1, the J component would be multiplied by A2, and the K component would be multiplied by A3. So if we implement those at this stage, we're skipping that step, and all we have to do is find the determinant of a single matrix, not the matrix, and then also take the dot product. So let's apply this. Calculate the volume of the parallelepiped if A is 1i plus 2j plus k, and B is 5i plus 2j minus 4k, and C is 3i minus 4j minus k. So we're looking to find A dot B cross C, which in this case is going to be defined as the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. So that determinant is well, let's fill in the entire matrix first. Let's not get ahead of ourselves. So that'll be 1, 2, 1, 5, 2, -4, 3, -4, -1. So substituting those all in, we're going to get 1 times the submatrix 2, -4, -4, -1, minus 2 times the submatrix, 5, 3, -4, -1, plus 1 times the submatrix, 5, 2, 3, -4. So finding the determinants of these three submatrices, we get 2 times -1, take -4 times -4, minus 2 times 5 times -1, take -4 times 3, plus 1 times 5 times -4, take 3 times 2. So that leaves us with -2 minus +16. So 2 minus 16 is going to give us -14. -5 take -12 is going to be 5 plus 12. That's 7 times -2 is -14. And then 5 times -4 is -20. Minus 6 is going to be -26. So this is going to give us -54. But remember, the volume of the parallelepiped is the magnitude of this product. So we take the absolute value of our 54, which gives us 54 units cubed. And I think above here, we should have had units cubed as well. So that's all for the video. Thank you very much.